Thanks, Avi. Great to be here. So I was under the impression this would be a computer science audience, but maybe it's not quite the case. So I'm going to speak about recent work and ongoing work actually with Asgar Jamneshan, who's actually in the virtual audience, and Shalom, who's in the front row here, well, our work has to do with the Gowers norms and also ergodic theory. And I decided to delete almost all the ergodic theory from the talk, but a lot of you who are experts may sort of interpolate and sort of see ergodic theory hiding underneath the slides. Okay, so I will focus the talk on the concept of a polynomial for finite fields.
Yeah.
All right, so our setup is that we are going to work in finite dimensional vector spaces. So we'll take a finite field FP of prime order, and P will usually be very small. So you can think of P equals 2, which of course the scientists that's very familiar. And we take a very large dimensional vector space FP to the n. So you think of high dimensional vector spaces over small fields. And over such fields, we have the notion of what I'll call a classical polynomial. So a classical polynomial of degree k, or at most k, strictly speaking, is a function of n variables in the field FP, which also takes values in FP. And it's just a sum of monomials where you take, so you have n inputs, which are in this field FP, and you multiply at most k of them together. And then each such monomial, you multiply by some coefficient in your field, and then you put them together, and that's a polynomial. Okay, so you all know what a polynomial is. This is specialized into the case of polynomials in n variables over a finite field. Okay, and of course it's a computer science. Okay, when p equals 2, these are essentially the same thing as reasonable codes. All right. So of course polynomials appear all throughout mathematics, particularly in more algebraic areas of mathematics. We're interested more in analytical questions, so we will often convert these polynomials into complex value functions by taking an exponential. So if you take a standard character, e of theta e to the 2 pi I theta, then any polynomial which takes values in f sub p, finite field, you can turn into a function that takes values on the unit circle inside the complex numbers by just dividing it by p to get a p through the unity, and then taking the exponential, or get an additive p through the unity, take exponential to get a multiplicative p through the unity. Okay, and so so such functions we will call classical phase polynomials of degree k. Okay, so these are the kind of multiplicative versions of polynomials, and they take values in p through the unity. And you should think of k as being really small. So for example, it was 5. The quintic polynomials over characteristic 2. In fact, that's a specific case I'll talk about later. Okay, and so just to give one example, okay, here's a classic, here's a phase polynomial in 2 variables, which is quadratic of degree 2. So it's some quadratic function divided by p, and you take e to 2 pi out of that. Okay, so these are all fairly familiar concepts. For the type of mathematics I do, additive combinatorics, it's been realized over the last 10 years, 20 years now, that actually it's more convenient to generalize the notion of a classical polynomial to what are called non-classical polynomials, which also take values on the unit circle, but are not restricted to be roots to unity, p through unity. So they're defined a bit differently. So the motivation is that there's another way to define a polynomial. So instead of decomposing into monomials, recall that if you have a smooth function, let's say of one real variable, a smooth function is a polynomial degree at most k, if and only if when you differentiate k plus 1 times, it vanishes. So a quadratic is a function whose third derivative vanishes, for instance. Okay, so motivated by that, we can define in the discrete setting, if you have a function still on the this vector space fp to the n, but now taking values not in fp again. So you don't take values in the field, but you take values in the unit circle, which is the sort of the fundamental group of Fourier analysis. Okay, so R mod z. So functions that take values in the unit circle will be called non-classical polynomials of degree k, if they vanish if you differentiate k plus 1 times, where differentiation now denotes discrete differencing. So for any shift h in your base vector space here, we denote partial h of p to be the differencing operator, where you shift f by h, and then you subtract by f again. So that's like a discrete version of derivative. And if a function which gets killed by any k plus 1 derivative discrete differences is said to be a non-classical polynomial, be k or less. Okay, and then just one technical thing, that the zero polynomial by definition, by convention, has degree negative infinite. So that's a non-classical polynomial, and a non-classical phase polynomial is the same thing, but you write it multiplicatively. So you raise it to e to the 2 pi I of a non-classical polynomial. It's called a non-classical phase polynomial.
Non-classical includes classical.
Yeah, okay, so it's maybe actually not necessarily classical if you want to be really pedantic, but okay, and strictly non-classical if you're not actually classical. But that's the terminology we came up with 10 years ago, and I'm not changing it now. Okay, all right. Yeah, so classical phase polynomial. So it's easy to show that every classical phase polynomial is a non-classical phase polynomial, and conversely, and a non-classical phase polynomial is classical if and only if it takes values in the p-through unity. So if you have a non-classical polynomial p, big P, and little p times big P vanishes, that's precisely, then it is basically classical. If you identify fp with the p-through unity, otherwise it's not. So it is a larger class of polynomials. Now, so for what I do, so if I don't say what a polynomial is, assume it to be non-classical or not necessarily classical. Okay, so I will not restrict attention to classical polynomials unless it's specific. Otherwise, so the definition is different, but they do share many of the same features. Just maybe the one notable thing you be careful about is that classical polynomials form a ring. If you multiply two classical polynomials, you get a classical polynomial of a slightly higher degree. But non-classical polynomials, that's not true because it doesn't make sense. You take two functions that take values on the unit circle. The unit circle is not a ring. It doesn't have a multiplication operation. It has an addition only and not multiplication. So it doesn't, you can't multiply polynomials by other polynomials. So that's annoying. But other than that, they are very similar. Okay. Some other remarks. Okay, if you're in what we call the high characteristic case, so if the characteristic P is higher than the degree, then actually the two constants are basically the same. One can show that all non-classical polynomials are basically classical plus a constant, which need not be a p-through unity. But yeah, so every constant, regardless of whether it's p-through unity or not, is a non-classical polynomial degree 0, just by definition. Any derivative kills it. But apart from that, plus c, so standard ambiguity, non-classical and classical are the same thing in high characteristic. And there's a slight variant if you're in almost high characteristic p equals k, then that's also true if, okay, so any non-classical polynomial, it might not be classical, even up to a constant, but there's always a hyperplane inside your n-dimensional space on which it is classical. So they're almost the same thing. But it turns out that in low characteristic, where p is less than k, and for example, p equals 2, which is of interest in computer science, that's pretty much everything is low characteristic. 2. Then there's the huge constants are genuinely different. There are non-classical polynomials that are of degree k, which are not at all approximatable in any sense by classical polynomials of degree k. They can be approximated by classical polynomials of higher degree, but not of low degree. Yeah, so if you have in the low characteristic case, you have a degree k polynomial non-classical, and you multiply by p, it doesn't vanish. Instead, there's a reduction of degree, but not enough to kill it. It turns out that if you have a non-classical polynomial of degree k and you multiply by p, it lowers the degree by p minus 1, basically. But it doesn't necessarily kill it completely unless you're in the high characteristic case.
That's an exclamation mark and not a factorial.
Oh yeah, sorry, yeah, okay, okay. That is a non-factorial symbol. Okay, yes, okay.
Not necessarily factorial.
All right. Okay, so yeah, so the general expectation is that the low characteristic case is hard. Even though F2 has lots of convenient features, there's sort of a trade-off actually in working in F2. There's good things and bad things about F2. All right. Okay, but for what we do, the low characteristic case is harder. All right, so just to give you some examples of non-classical polynomials. Okay, so we'll work exactly in the F2 case. So in F2, we define a very simple map. I'll call the absolute value of an element in F2 to be its represented in integers from 0 to 1. So 0 mod 2, the absolute value defined to be 0, and the absolute value 1 mod 2 is 1. So it's just if you like it's taking mod 2 as a computer software rather than as a mathematician. Okay. Then degree 0 polynomials are just constants. So any element of the torus is a degree 0 polynomial. A degree 1 polynomial is a linear thing, so it's a constant plus you can take monomials, you take absolute value of x1 over 2, so that's 0 or 1/2 multiplied by various integer coefficients. And that is what a typical linear polynomial, non-classical linear polynomial looks like. And it's basically the same concept as a classical linear polynomial, except that in the classical case, theta also has to be a mod of 1/2. Degree 2 polynomials, so the first term would look kind of familiar. It's you have quadratic monomials, x1, xi, xj times integer coefficients over 2, but then you're also allowed to take linear coefficients now, but now over 4. So, for example, even in one dimension, there's a non-trivial example of a quadratic. The function that takes 0 at 0 mod 2 and 1/4 at 1 mod 2 is a quadratic function of f2. If you differentiate it once, you get something that looks like 0 and 1/2, or 1/4 minus 1/4, actually. And you differentiate that twice, you get constant 1/2, 1/2, 1/1, and 3 times it will get killed. So that's you can start seeing that that you no longer take values in the square root of unity. Now it takes values in the fourth root of unity plus a constant. And then cubics, it gets more complicated now. They can actually take values in eighth root of unity plus a constant, and so on and so forth. So we actually have a complete description of what the polynomials look like. They look like sums of monomials, but the monomials, the coefficients are slightly weird. But they are in principle understood. Okay. All right, so these are the polynomials and the phase polynomials. And what I'm interested in is how these classes of functions relate to all the other functions on this finite field vector space. So take any other complex function on this finite field vector space, but we're only interested in functions that are one bounded, which means that their magnitude is the most one. So if you like functions taking place in the complex units. Okay, so any such function. Okay, so you can think of it as some word or signal. I mean, but I don't. I'm not part of applications, so for me, it's just an abstract function. So the type of questions we're going to discuss here are what I will call a 99% inverse theorem and a 1% inverse theorem for reasons I'll not really explain. But okay, so the 99% inverse theorem question is: so if I have such a function, when is it close to a phase polynomial? So when can I, like, given an epsilon, can I check whether it's within epsilon of a phase polynomial? Like, when is it behaving like a phase polynomial 99% of the time? Okay, and if I have a criterion for that, then I will call a 99% inverse theorem. And then what I call a 1% inverse theorem is how can one tell that f is not close to a phase polynomial, but at least correlates with a phase polynomial, which means that its inner product is at least 1%, 0.01 in absolute values. So and so there's a natural L2 product on this space. So when are you not completely orthogonal to a phase polynomial degree k? Okay, and we would like to criterion for that. Okay, and that I'll call a 1% inverse theorem. And then after you ask these two questions, I'm also interested in what you might call an algorithmic inverse theorem. Okay, so if you know that f is close to a phase polynomial, or if f correlates to a phase polynomial, how can you find that phase polynomial? Is there some algorithm that's pretty fast that can actually find it? Yes.
Just for the computer scientists, the 99% in this theory, this is unique decoding regime.
Yeah.
And the 1% is least decoding regime.
Okay, thank you. Okay. Yes, thank you. I don't speak the dialect so well of computer science, so I'm glad to be here. Okay. Yes. You said what was the first one?
Unique decoding.
Unique decoding and list decoding. Okay, that's good.
Very easy to come out in what you say.
Okay, sure. I also know that you like to use 51% instead of 1% sometimes. Okay.
You are the author of 1%. I like.
All right. Okay. All right. This is the dialect of additive combinatorics, which is the dialect I speak. Okay. All right. Okay, so it's just some general remarks. Okay, if I make a completely random function on FP, then you can use various standard tools like the Shalom inequality, and most functions are what we call pseudo-random, which means that the correlation with all these these phase polynomials are basically exponentially small. There's not too many of them of these phase polynomials. I mean, they get a bit more as a degree, but as long as the degree stays bounded. Okay, so most functions are pseudo-random. Some functions are not. But there's all kinds of useful structure theorems, which I won't talk about here. But roughly speaking, any bounded function can be kind of split up into a structured piece, which is maybe some finite linear combination of phase polynomials, and a pseudo-random piece, which is more or less orthogonal to all these space polynomials. Sometimes there's some extra small errors, and there's these, sometimes you want extra properties, like if your original function is non-negative, you want some of the other components to be non-negative as well. There's lots and lots of useful structure theorems. They're often proven by tools such as the harmonic theorem, and they're also related to the similarity regularity theorem in graph theory, you know what that is. But I will not talk about any of those. But that's a very useful consequence of the inverse theorem that is useful for many applications, but we are not going to talk about that. The higher degree case is a bit more complicated than the linear case. So in the linear case, Fourier analysis is very, very useful. And the fundamental fact in Fourier analysis, if you take two linear phase polynomials, then they either differ by constant or they're completely orthogonal, and there's no middle ground. And that makes Fourier analysis really, really nice. It's a study of orthogonal systems. And so we understand Fourier analysis really, really well. The situation is more complicated in higher degree. So if you have 2 degree K phase polynomials, then they might correlate and they might not correlate, but the only way that they can correlate is not if they differ by a constant, but if they differ by something that's low rank, which means that they can be expressed into, the difference is expressible in terms of lower degree polynomials in some efficient way. And there's a long story there, but I think there are other talks in this program that will be devoted to that, so I will not talk about that. Okay, I think I already mentioned this. In high characteristic, non-classical and classical polynomials are essentially the same. In low characteristic, they are not. So let me just give you one model example. So here is a non-classical cubic in F2 to the n. So in F2 to the n, if you take this function, so you basically, you take a binary string of n zeros and ones, and you count how many ones there are. So you just sum all the absolute values. So you count how many ones there are and in your string, and you take that 1/8, divide by 8. So that turns out to be a cubic polynomial in the non-classical sense. That's the real computation. Every monomial is cubic, and that's direct computation to sum it up. So this is a genuinely, not strictly non-classical polynomial of degree 3, in that it doesn't look at all like a classical cubic polynomial. Every cubic polynomial has a negligible correlation with this guy. Instead, it is actually connected to classical polynomials of degree 4. So you can write this non-classical cubic in terms of a classical linear function, which is just the first elementary function. You just sum all your coefficients, mod 2. There's also the second classical elementary function. So you just sum all the pairs of products of just mod 2. And then there's the fourth elementary function, where you do it 4 times. And then by an application of a classical formula called Lucas's theorem, you can show that this cubic can be written as a linear combination of as some simple combination of these 3 classical functions, but the degree has gone up. Okay, so this is cubic, but you want to express it classically, you need to introduce a quartic. Okay. And that's still the general principle. Yeah. So in general, any non-classical polynomial degree K can be expressed in terms of classical polynomials of degree a bit higher than K. Okay, so I talked about these inverse theorems, or list decoding and so forth, if you wish. So let's look at really simple examples first. Okay, so suppose you want to solve these questions for degree 0. Okay, so this is the easy case. Okay, so the only phase polynomials in this case are just constant functions. Okay, so now you're asking, when are you close to a constant, or when do you call it a constant? Okay, and then there's an obvious statistic to measure this. Okay, and this reasons that become clear later is called the U1 Gowers semi-norm. Okay, so you take a function f on your vector space, and you take its average and takes absolute value. So you just take the average of its mean, and that's called the Gowers semi-norm, U1 semi-norm. And this tells you everything. Okay, so what's easy is that if you are one-bounded, this mean is at most 1. And it's only equal to 1 only if and only if you have this constant. That's triangle involved. And it's also easy to show that it's a 99% version. So if your U1 semi-norm is bigger than 99%, if it's very, very close to 1, then you are very close to a constant phase in L2 sets. That exists some phase which is little over 1, just in L2. Yeah. And that's just cosine rule, basically. Little over 1 is anything goes to 0 as eta goes to 0. Okay, so that's really easy. And also easy is a 1% inverse theorem. If this Gauss semi-norm is bigger than 0.01, then you correlate with inner product 0.01 with a constant phase, and that's actually just tautology. This is a good definition of G1 norm. Okay, so that's this completely answers the theorem, these inverse theorem questions. Okay, but the question is: suppose you have these correlations. Okay, what is this phase? How do you compute it? So there's various ways to actually find this phase. So first of all, this U1 semi-norm you can estimate probabilistically very quickly. So even if you're in a huge dimensional vector space, instead of taking the mean over the entire vector space, which is p to the n of different points, you can just do Monte Carlo integration or just random sampling or empirical averaging, depending on what dialect of mathematics you speak. And it's you just pick a random subset of f p to the n, and you just sample f at a random number of points, and you take the average, and what is it? Will tell you that for high probability that will converge to your mean. So if you want to compute this expression with to error epsilon with failure property epsilon, you just need to sample some polynomial number of sample points, and you can get this mean quickly. And very similarly, if you want to actually find the phase that's closest to f or reasonably close to f, you can just again take an empirical mean, just average f 4 times. If you are close to if your Gowers norm is large, this mean will be close to the inner circle, and you just round it till you just take the point in the inner circle that's closest to this empirical mean, and that will almost always be a phase that actually is close to your function. Okay, and you can compute in polynomial time in all the parameters. Okay, so that's okay. This is all simple. This is undergraduate statistics, basically. Okay, now we move on to the degree 1 case. Okay, so degree 1, the polynomial phases are basically constant multiples of the Fourier characters. Okay, so every vector in the dual group, which is also fp to the n, gives you a Fourier character. So it's e to a linear phase. The analog of U1 norm is something called the U2 Gowers norm. So instead of taking the mean of f, you take the mean of this expression. You take f and 4 copies of f, and so you average over all parallelograms: x plus h, x plus k, x plus h plus k. You take all the parallelograms in your vector space. In F2, it would just be 2-dimensional subspaces. And you multiply F 4 times, and for technical reasons, you put a conjugate on 2 of them. And you take this average and you take 4th root. And that's called the U2 norm.
This is the notation before taking derivative with respect to h and k.
I will give the alternative. Okay. Yeah, there is, okay, yeah. So for U3 and U4 and so forth, it's much more unruly to actually use this relation. Yeah, so there's a more complex notation, which I will describe later. I'll just mention that the U1 norm has a similar representation. If the square of the U1 norm is a similar type of average, except that you only average over 2 f's rather than 4. Okay. So this is an expression called the U2 Gowers norm. It turns out to be a norm. I won't prove it here. Well, actually, it follows from this observation. So if you play with Fnpover's theorem a little bit, you can show that the U2 norm is basically the L4 norm of the Fourier coefficients. So it's very, very related to the Fourier transform. And because of that, you can get the analogs of everything I just said in k equals 0. So if your U2 norm, if you have a function which is 1-bounded, the U2 norm is always at most 1. And it's only equal to 1 if your function is a linear phase polynomial. And that's really easy. I'll prove it here though. If your U2 norm is close to 1, bigger than 99%, then you can show that there's a linear phase polynomial which is really close to f in L2 norm, and with something which depends polynomially on eta. They didn't phrase it quite this language, but this is basically due to Bloom-Theory control, at least in the okay, it's the same argument extends into this language. Okay, so that's true. And then if your U2 norm is just a little bit big, like bigger than 0.01, then f has some correlation, maybe eta squared correlation with a linear phase polynomial. Okay, and conversely, if you eta correlate with a phase polynomial, then your Gowers norm is like bigger. So up to like a little square, this norm completely detects when you correlate with a linear phase polynomial. Okay, and this is an easy application of Fnpover's theorem, which I will not take here. Okay, so that's so the inverse theorems are all easy, and then the question is whether is the alchemy questions are what's left. Okay, so again, using a similar random sampling technique, you can compute any of these norms in polynomial time to accuracy epsilon, no matter how big your vector space is. I mean, assuming that you can a computation model where you can sample randomly elements of your space by some oracle or something. All right, now suppose you know that you're close to a polynomial. How do you actually find the space polynomial? So let's, for simplicity, consider the classical case. Suppose that your phase polynomial is actually takes place in P3 unity. If you have a polynomial and you want to find its value at some point, but it's only given in some noisy sense, like every single time you sample it, it might differ by an epsilon or something. You can still clean it up or do unique decoding if you wish, because if you're linear, then you can, given any parallelogram, so given any point x, you take a parallelogram based at x, and you can always write the value of your linear polynomial at x in terms of the value of the linear polynomial at the other 3 points of the parallelogram, because the alternating sum is 0. And that's what it means to be a non-classical linear polynomial. So if f is really close to E of p, then E of p at any point x is also some alternating combination of E of p at 3 other points, which you choose at random, basically. And those will usually be close to the corresponding values of f. So usually this E of p of x will always be close to or the same as this combination of f. And so now you can use this to recover E of p. So what you can do, you want to evaluate this polynomial at a given point, you just take lots and lots of random parallelograms based at this point, you compute this quantity, and 99% of them or 97% of them will all give you the same prediction. And so you just poll 100 of these guys, and you take a majority vote. You say whichever number of these predictions vote for, that is what I will predict E of p to be, and that will basically work with really high probability for any given point.
In the 99% case.
Yes. Okay, and I'll talk about 1% case presently. Yes. So this gives you what you might call a way to evaluate E of p as an oracle. Like you can evaluate at any given point in bounded time, depending only on the error rate, failure rate that you want. Okay. Yeah. So what about in the 1% world? So then we have this result of Gowers Uk and Levin, that if you have a function that only correlates 1% correlates with a linear phase polynomial, you can still find it in time, now polynomial in the dimension of n. There's a algorithm polynomial time in the dimension of your space that recovers your function. And in fact, you can recover all the polynomials that correlate with the function. Okay, so that's an result of Gowers Uk and Levin. But actually, you can do a little bit better. You can remove the independence in the following sense. If you just want one function that correlates, you can find one function that correlates, but not written as in terms of monomials, because even just writing down the monomial expansion takes polynomial time to even write it. But if you just want to represent your phase polynomial as an oracle, that given any input, you can just figure out what its value is in bounded time, you can do that. So there is, as long as you sort of represent your function in a slightly weird way, you can actually do it in bounded, you can actually recover this E of p in bounded time rather than polynomial time. And let me just very quickly sketch why this is true. So suppose you have a function which has this large U-turn, so it correlates at least one linear phase polynomial. That's one large Fourier coefficient somewhere, maybe several. So now what you do is that you pick some medium-sized random subset H of shifts, and you start convolving F with various weights, which you call modifiers, supported on this small random set. And the effect of this modifier is it suppresses some of the Fourier coefficients and keeps the others. And it turns out that if you pick enough random shifts, you can find a modifier that basically isolates one Fourier coefficient and damps out all the other ones. And so when you do that, you can actually find a convolution where the usual norm is now basically 1. And you can keep it one bounded, and you can find a convolution which is basically really close to a single. You can turn a 1% correlated function to an agnostic correlation function by some suitable finite convolution with a small filter.
That happens in all risk decoding algorithm.
Oh, okay.
Yeah.
Okay. No,
Yeah.
I don't know a specific. This I would call folklore. This is something which, I don't know what this is written up, but yeah. So yeah, you apply some filter, and there's some bounded time algorithm to find such a filter. And then you've turned it in that Hampson mode, and then you apply the majority vote method from the previous slide to give you. Okay, so okay, all right. So algorithmically, you can get a very good representation. From a more analytic point of view, one thing this tells you is that the inverse theorem is not only algorithmic; it's also what I call measurable. That if you correlate it with some linear phase, then not only does this linear phase exist abstractly, but and not only can it be somehow obtain in an algorithmic sense efficiently. It's what I call measurable. Okay, the precise definition of measurability involves a lot of quantifiers, which I will not detail here, but roughly speaking,
I have a question.
Yeah.
So the H you had in the previous slide, that enhances one of your, so you choose H randomly of the size that you had before, and that enhances one of the Fourier coefficients. So
yeah, you choose H randomly, okay, and then you get to pick weights. So for every frequency shift H, you can pick a weight, lambda H. And I claim that there exists a choice of weights on this H, which will retain one of these Fourier coefficients and damp out all the other ones.
The choice of these weights is you choose them randomly. So how do you find?
You have to find it. Okay, so you choose a weight so that the Gowers norm becomes really good, and so you can just do a brute force search over all the possible choices of weights until you find one that is 99% close to a phase polynomial, and so at least one exists, and so you can do a stupid brute force search. That's still technically bounded time. It's not a good one. I'm sure there are better ones, but.
Yeah. Okay. Never mind. I'll ask you later. I'm not sure I understand how you choose these. Never mind. I'll ask you later.
Once you know it abstractly exists, you just do a search. You just brute force search for it. At the time,
suppose your function f had like all the Fourier coefficients were the same size. You know, it has like 100, and they're the same size. What is this function h? How does it isolate one of them?
So every shift, like if you had characteristic 2, so every shift. When you average along that shift, it will kill half of those 100 frequencies and keep the other half. If you average in one random direction, so you can do that a few times, and you can eventually just isolate one survivor.
Okay, we'll talk about that. Fine.
Yeah, it's like you have 100 identical-looking students. You just get them all like out of random true-false questions, and designs that half of them fail. And eventually you pick the one student that you want. Maybe that was not a great analogy, but yeah.
That's a way to find them all. I mean, you'll find.
You can also find them all. Yeah, okay. You run multiple tests, and you can eventually find all. Yeah. Okay. Yeah, but for example, it's classical that you can have a Lebesgue measurable subset of say the plane, right? Then you can approximate it, but it's very close to a union of rectangles. Right? That's kind of what it means to be measurable. And so there's a sort of similar thing going on here. So the linear phase polynomial that correlate with f, because of the existence of these bounded time algorithms, it means that these every single one of these linear phases is measurable in the sense that for every epsilon, you can approximate ETF by some combination of bounded number of translates of f. There's some function, nonlinear function of within epsilon of your phase. Now, I don't want to make that more precise because when you expand it out, there's a lot of quantifiers. The same way that what it means to be Lebesgue measurable is a lot of quantifiers. Expand it out. But somehow this lies in in the sigma algebra generated by f. But that doesn't make any sense in the finite world. But if you jump to the ergodic world, then there's a way in which this makes sense. But I do not want to talk about ergodic theory. Okay. All right. Okay. So now that's degree 1. So now let's talk about higher degree. So for k=1, linear Fourier analysis basically answers every question. So for k bigger than 1, it's been realized for decades that linear Fourier analysis it's not the right tool. So there's this more difficult theory of higher order Fourier analysis, which is basically introduced by Gowers 98, which in principle answers these questions, but we're still working out some of the details of this theory. And quantitatively, it lags linear Fourier analysis in many, many ways. But many of the things I talked about still have analogs. So they're the higher order. So for degree k polynomials, the correct norm to consider is what's called the UK+1 Gowers norm. And now you average over k+1 dimensional parallel pipets, and you take k+1 multiplicative derivatives of your function. So for every function f, taking those as complex numbers, there's this multiplicative derivative where instead of taking differences, you multiply f x plus h by the complex conjugate of x. That's called the multiplicative derivative of f. You do that k+1 times, take average of that, take a root, and that's called the UK+1 norm, which actually happens to be a norm, and this generalizes the U1 and U2 norms that we talked about. And many of the things that I said before have analogs. So if you have a one-bounded function, UK+1 norm is at most 1, and it's only equal to 1 if you're exactly a degree k phase polynomial, and that's not too hard to prove. If you are close to 1, 99% close to 1, then you are very, very close to a phase polynomial. Okay, and that was essentially proven by a long time privilege later on in a different language, in the classical case. Okay, but this particular statement actually was I sent myself. And again, you can use majority vote, and you can actually find this polynomial in bounded times in Oracle. Right? All right. In particular, this EV is kind of measurable restricted to F in some sense.
The data deteriorates exponentially with K.
Probably the way we do it, yes. I don't know necessarily. It's not. Okay, I can believe that. Yeah, for everything I discussed, K is bounded. We do not consider dimension K. Our methods are well. Okay, but so the 1% case is true, but it's a difficult theorem. So it's one thing I can put in a block. Okay, so if a function has a Gowers norm of at least say epsilon, then you do correlate with a phase polynomial of that degree. But that's hard to prove. So there's now lots of proofs, and special cases have special proofs and so forth. It's particularly hard to prove in low characteristic, but okay, I could give a talk just like there has even probably has been a talk just on this, but okay, but it's a known theorem. Okay, okay, so those are the inverse theorems, and then what's the algorithmic situation? So Gowers and Levin showed that if you correlate with a linear phase polynomial, then you can find it in polynomial time. That's also known quadratically. If you call it quadratic polynomials, you can find that in polynomial time. That was worked out by Stanley Wolf in 2001. Basically, because they found that this inverse theorem, I just said, the U3 version, they found the algorithm. And then that was extended one more degree to cubic a bit more recently. Okay, so the Gowers theorem has been at least partially extended. So here. Now, okay, so there's an it's buried in a paper of Tammy and myself that there's a certain ergodic theory claim, which, as I said, I want to minimize the role of ergodic theory. So I'll just say some meaningless words. Okay, every ergodic FP omega system of order K is an Abraham system of order K. So there's some statement in ergodic theory which, if it was true, it would imply not the inverse theorem. And it also implies that the polynomial that it correlates to function is measurable in this technical sense that I alluded to before. So there's an ergodic statement that gives you this measurability. And it would probably give you a Gowers-Leibniz type result as well. I haven't fully checked whether that's the case. Yeah, so there's some good statement in ergodic theory, which I don't want to formalize, which gives you everything you want. And it's true in some cases. So Vitaly, Tammy, and I, we proved this good ergodic theory statement in high characteristic. And as a consequence, we were able to prove this Gauss in high characteristic, and we get this measurability, and we get this bounded time approximation, and so forth. And then it was extended a little bit. So bigger in case what we did, and then many years later, it was pushed a little bit down to a slightly less high characteristic. Okay, but so finally, the new result, which we are still writing up, so this will be in the archive soon, is that this conjecture, unfortunately, is false in low characteristic. We don't know exactly which low characteristic is false yet, but we have a specific example. So when p equals 2, k equals 5, you want to call it quintic polynomials in F2. This ergodic theory statement, which I haven't detailed, is false. But the practical, there's a stronger version, which is, so the combinatorial consequence of this is that if you have a function on F2 to the n, which has large U6 norm, right? So we know from this inverse theorem obtained with great effort that this function must correlate with a quintic phase. But this quintic phase, it exists, but it is non-measurable. There exist functions f on very large F to the n with large U6 norm, where the quintic phases that correlate with this function, none of them can be expressed efficiently in terms of a bounded number of translates of it. And if I was to expand this out properly, there'd be like 5 quantifiers, and I don't want to do that. But yeah, so this inverse theorem, the map from the function to the polynomials that it correlates with is non-measurable in some sense. Now, what remains open? So this may mean that the Gowers-Leibniz theorem is false. it doesn't, the implications don't quite go. So it's possible, therefore, that maybe the Goldberg line breaks down in such high degree. This is still open. There is progress. Milicevic does have a new proof of the specific U6 F2 in university. And it's possible that that theorem might give a polynomial algorithm. This is something which is still unclear.
Allow it to be polynomial in N also.
Yeah, there may be a polynomial in N. What this tells you is that there's no bounded time independent of N algorithm to find P, but there may be still polynomial in the dimension of your space algorithm. I don't know. Okay, so that's an open question. Okay, so right, so this was a surprise. Yeah, it's what to ask. We will try. So the way we found this actually is that we're trying to prove this conjecture, you can make these ergodic reductions, and it reduces to the statement in group cohomology. You have to show that certain co-cycles, the space of co-cycles is the same as a certain space of co-boundaries. And it turns out that in this finite field setting, these are just finely generated groups. So there's these two very concrete finely generated groups. There's just two pools of integers that obey a system of integer linear system equations. And you can just if you play around with normal form and so forth, you can get a computer to actually check whether these two spaces are the same. And so we started with with small dimensional cases, and we could check that they're the same, they're the same, they're the same. This is curse of dimensionality that every time you go up a degree or something, it takes exponentially harder to actually compute this. And just before we ran out of computer power, we found a counterexample. And it was this, and then we had to. Okay, so we have this abstract counterexample, this numerical counterexample, and then to convert it back into an actual comprehensible counterexample took more work. But we actually eventually translated this numerical thing into a human verifiable counterexample. So I can tell you the specific function. So there's a specific function on F2 to the n, actually a random specific function, which has large U6 norm. It correlates to a quintic, but you can never find this quintic measurable, or almost never find this quintic measurable.
So what does it mean? Because you say bounded, the bounded number of shifts of F. Bounded, how do you roll out there? Bounded, do you roll out?
I really didn't want to list the quantifiers. Let's see. Especially when you negate it. Okay, so for any epsilon and a k, not k, for any epsilon, like if you give me an error target, it points to a 1, and give me a number like 1 million, and I will give you 1 million shifts of this particular function. You will not be able to approximate this function, the quintic that it's called, correlates with, by any function of these 1 million shifts to within 0.01.
It's the same, but it will be the same function.
Yeah. So
it's not a function.
Yeah. So for any sufficient large dimension n, there is a random function which with high probability does what I just said.
Okay. So then the n will depend on the million, but
yeah.
Yeah. Okay. Good.
Yeah. Yeah.
So there's a family of functions like with n that will roll out any bounded explanation.
Yeah, I mean, the way we actually prove it is we pass through a limit when n goes infinity, and you can use ergodic theory, and things are a lot cleaner. Half the quantifiers go away, and you do the other half. But I didn't want to talk about that. So instead, I'm lying. Okay, basically. Okay. All right. So the precise construction. Okay. So I mean, the explicit construction actually turns out to be relatively compact. So what you do is that you take a random cubic polynomial taking values in z mod 4z, and a random quadratic polynomial taking values in z mod 2z, and a random quintic polynomial taking values in the 32nd resolution. Don't ask us why this works. This is just what the computer tells us is the first thing that works. Okay, so you take these three random objects and you form this combination. So R is an element of z mod 4z. R choose 2. Is well defined as element of z mod 2z. So it turns out that the second binomial coefficient, if you want to know its parity of R mod 2, you only need to know what R is mod 4. So R, because R mod 2 has a division by 2, it's R times R minus 1 divided by 2. So because it's division by 2, it's not quite defined as a map from z mod 4z to z mod 4z, but it's defined as a map from z mod 4z to z mod 2z. So you take R choose 2, that collapses z mod 4z to z mod 2z, then you can multiply it by z mod 2z, that's a ring, and then you divide by 2. So you take this weird expression and then you shift it by this random quintic. So this is a random quintic shifted by a complicated low rank object. So low rank because it's a function of lower degree polynomials. It's a function of a cubic and a quadratic. But it's actually higher degree than P. As a polynomial, this expression is actually sextic. It's degree 6, it turns out. So it's high enough degree to somehow obscure P. It makes it hard to see P from F. But because it's low rank, it doesn't really, this guy still correlates with P. In fact, it's equal to E of P like 75% of the time. So this is our counterexample. So it turns out that this object is close enough to E of P that it has large Gowers norm. In fact, this one has an explicit constant. It didn't work out. So and it correlates with quintic. And in fact, the precise quintic it correlates with is E to P, and that's basically the only quintic it correlates with up to lower rank errors. So we know. I mean, from this formula, we know what it should correlate with. It's E of P. But the thing is, E of P is not measurable with respect to adding this extra term adds enough kind of interference to F that you cannot see. You cannot reconstruct P. So it turns out that if I give you F and you do all this random sampling of a million shifts and so forth, you can reconstruct Q, it turns out, and you can reconstruct twice R without much difficulty. But see, twice R, that tells you the parity of R, but it doesn't know R14. So it doesn't know what R choose 2 is. And so that's not quite enough information to, like if you knew what R and Q were, you could subtract out this noise term, recover P. But you only get to discover twice R. That's measurable. The basic problem is, the key problem is that if I have R is cubic and 2R turns out to be quadratic. Multiplication by 2 injects to the lowest degree by 1. The basic question is that if you have a quadratic polynomial, so abstractly, it turns out that every quadratic polynomial has a cubic square root. Every time you have a quadratic polynomial, you can just manually write it into coefficients and divide each coefficient by 2. And on the torus is a divisible group. Every element of the torus has at least one square root, like that's true. And by doing that, you can take any quadratic polynomial and take a square root, which is cubic. So abstractly, it exists. But the reason why, morally, the reason why UP is non-measurable is because the square root problem turns out to be non-measurable. So this was an older observation of Tammy and myself, that if you have a quadratic polynomial, you can always square root it to a cubic polynomial just by computing every single coefficient and taking the square root. But there's a lot of coefficients. There's polynomially many. It's not an operation that is measurable in any sense. And in fact, you can actually prove using some algorithmic theory calculations that in general, this is not a measurable operation. That there's no measurable way to take a square root of a quadratic and get a cubic. You can take the square root of a quadratic and get a quartic measurably. But you can just map 0 to 0.14 and 1 to 1.14. And that would actually give you a quartic all the time. But if you want the right degree of cubic, you have to decide sometimes 0 has to map to 0.2, sometimes map to 2.4. So 0.4, 2.4. Sometimes 1.2 has to map to 1.4, 2.4, 3.4. Sorry. And deciding exactly which to pick, we can't do in bound of time. Yeah, there's somewhat the global problem. If you do something global, like compute all the coefficients.
Global, but can you do it in polynomial in n time? This particular.
Good question. Probably. Which then suggests that maybe the Goldrick-Leibniz theorem is actually true. So for example, there's this result of Milosevic where he actually did do a fairly quantitative proof of the U6 F2 inverse theorem. And he didn't quite use this root statement, but there was a similar statement that he used as one of the key constructions in his argument. And so it's possible that if you just go through that 50-page paper or something, and you check that every single operation he does is somehow polynomial time in the degree, it's possible that you could get the quantitative, the Goldrick-Leibniz. So this has only been up to U4 so far, and that was just done last year. So I can predict, maybe that's a good question for somebody who's, I can predict this results, but we didn't do that. Okay, but yeah, we just at least have the surprising fact that it was non-measurable, and so in particular, there's this conjecture of Vitali Tamina, which we thought sort of organized this whole field is not quite right. So something weird is going on in high degree and low characteristic. And so it's ongoing work exactly what is going on, but we have at least one example of something bad is happening. Okay. Yeah, okay, this is it. Yeah. So it's still open whether this polynomial timeout. I think that's it. Thank you very much.
Questions?
Can I ask
Yes.
a question which relates to what I was trying to push for, the bracket polynomials?
Yes.
Would they provide new interesting examples?
Yeah. Okay. So really for the bracket polynomial is usually depending on the integers. So a normal polynomial might look something like alpha, taking those say the reals. Bracket polynomial looks like that. It's a bracket polynomial. These are say real coefficients. So this is a classical polynomial. But a bracket polynomial, you allow yourself integer parts, and maybe you do something like this. Okay, and this is just the fractional part operation. And so, yeah, so the analogous questions over the integers are what we consider finite fields, and it turns out that classical polynomials are not enough. You need these bracket polynomials, or equivalently, some category no sequences. That's a whole other story. Yeah, so it's not exactly the same thing, but these absolute value functions, to me, they are kind of like these bracket polynomials. Like these absolute values that show up here. So they are somehow baked into this theory. It's not exactly the same. So one of those long-running projects Asgar and all have is to somehow unify the finite field theory with integer theory and have some consistent theory that works for all abelian groups and explains why on this side you get no sequences and bracket polynomials, on this side you get classical and non-classical polynomials. We're edging closer to a unified theory because we're mostly finding counterexamples, which is kind of annoying. But hopefully there's still some unified statement.
So is there a chance that things of these creatures of this kind can be represented? That's actually very nice, clean representation. I don't want to spoil it, but suppose you could represent this one and similar ones by just semi-canonical, algorithmically defined bracket polynomials with maybe integer parts rather than fractional parts, which is, of course, the same.
Yeah. Yeah, there probably is a theory. I mean, we keep finding lemmas and stuff which sound like corners of a classification. There are some things that look a bit like no manifolds that are emerging. So like all these polynomials, we have a recent result still being written up that so a no manifold is a quotient of one big group by some lattice, some no-potent group by lattice. So we have systems where you take a no-potent group, but not a Lie group. Now it's a profinite thing, it's kind of nasty. You quotient by some closed and co-compact but not discrete. So it's not a lattice. We quotient by something. But then, yeah, I also have a quotient on. So that's a quotient on the right. But you also have a quotient on the left by a compact group as well. We have to get a factor. We have to take factors of no manifold type things, and some subgroup that is normalized by the action. And so we call these double coset systems. And all these polynomials and stuff, they are measurable with respect to the ergodic systems that associate these functions come from the double coset systems, but the polynomials sometimes live in extensions. You have to remove this double coset system, go back up to a single quotient. And the polynomials live there, and they're not measurable in the factor below. And that's the reason why we have these results. So this somehow, this extra coset doesn't show up in the integer theory because there's this fact that any factor of a no system is again a no system. But the weird thing is that we don't have a good proof of that fact. I think pretty much the only proof I know of that statement I just said is you have to go through the whole host graph theory. And that statement may actually be false in general. The analog of that into other groups, we've been flipping back and forth on that question. And that's a big stumbling block in sort of unifying all this theory together. So we keep finding counterexamples rather positive results, which is still nice, but yeah, we don't. There's a lot of question marks.
More questions? Okay, thanks for that story.